Ok. Sì, si sente. Ok.
So now we are in gamma rays. Please,
Yeah.
Lucia.
I'm going to talk about the indirect dark matter search at the Galactic Centre with H.E.S.S. I will focus on the first part of the talk, on the analysis of 10 years of data taken by H.E.S.S. looking. Okay, looking for monoenergetic gamma lines. Analysis that has been published in May. And in the second part of the talk, I will focus on a new S-like mock analysis that we have made to test the latest calculations for the WINO, and that is going to be published in these days. So to start, the high energy spectroscopic system is an array of 5 image atmospheric Cherenkov telescopes. It is set in Namibia, and it started in 2003 with the phase 1 with 4 telescopes of 12 meters diameter, which are here. We could span an energy range between about 100 GeV and 100 TeV with an energy resolution of 5% of the energy and an angular resolution better than 0.1 degrees. A field of view of 5 degrees and a flux sensibility 1% of the Crab Nebula in 25 hours for a point-like source at the zenith. Then in 2012, with the phase 2, we added a 5th bigger telescope in order to lower the energy threshold. This picture summarizes our detection principle. We have our very high energy gamma ray source. The photons travel straight to us. They enter the atmosphere. They start an electromagnetic shower, and the electrons and positons of the shower are relativistic enough to produce Cherenkov light. And when a telescope falls inside the Cherenkov light cone, there's a detection. And we are able to reconstruct both the energy and the position, so we can make both spectroscopy and morphology, exploiting the spectroscopic system. And this is what we see in our cameras for photons, hadrons, and muons. And then we want to distinguish our photons, and we do that mainly using the shape of the shower. We use a parameter that we call shower goodness. Here you have a distribution of events as a function of the shower goodness. This is a signal, and this is a background. And when we put a cut in the shower goodness, we can reject our background, and we have here a small amount of misidentified hadrons, which are what we call the residual background, and that we want to measure. For the dark matter search at the Galactic Centre, we choose a region of interest to look for the signal, which is a disk of 1 degree around. Oops. then we. Then we split it in 7 subregions, which are rings of width 0.1 degrees within a radius between 0.3 degrees and 0.9 degrees. This region is really promising, but it's also really crowded in very high energy gamma rays. There's diffuse emission like the ridge emission, the peratron, and there are sources like the central emitter, Sagittarius A star, and H.E.S.S G1745303. And so, since these are contamination for our analysis, we want to mask them and exclude the galactic plane and the main sources in the field of view. Then we want to measure our background, and we have to do it in other regions that we call off regions. And to explain the reflected background method that we use, I will use this picture. Here we have a map in galactic longitude and latitude, and in the z-axis, there's the J factor to give an idea of the intensity of the dark matter signal that we may expect. So here we have one of our regions of interest, one of our rings. Here there's a specific point in position, and we build the off region symmetrically to the on region with respect to the pointing position. Then we repeat for all the rings and for all the pointings. In this way, we have the same observation conditions, and we also don't have to add acceptance correction because we have azimuthal symmetry. And then we have to pay attention to exclude the same regions both in the signal region and in the background region to be sure that we have same solid angle size. And in addition, we exclude all the areas where the off region is closer to the galactic center than the on region to maintain an important dark matter gradient. Okay, this is similar to what has been shown for neutrinos. We look for gammas in the final state of dark matter annihilation. And when we compute our photons flux, we have a particle physics term that includes the dark matter mass, the thermally average velocity weighted annihilation cross-section, and the spectrum. Here there are some annihilation channels. And in our latest analysis, we focus mainly on the monoenergetic gamma line that here I'm showing spread for different energy resolutions because this channel is depends a lot on the energy resolution of the experiment. And then we have our physics term, so the factor. We focus mainly on Cosby profiles because our reflected background method cannot be applied to large cores. And in specific, we chose the INASTO profile for our analysis. And then we compare the measurements that we have in the on and off regions, and if there's no excess, we can put constraints on the annihilation cross-section. And to do that, we use a two-dimension Bindel likelihood approach because we want to exploit the peculiar spatial and spectral features of the dark matter that make it distinguishable from the isotropic simple parallel background. And so here we have our likelihood function. We have a Poisson term for the on region, a Poisson term for the off region. And on and off are the measurements in the on and off regions, and S and NS prime, the expected signal in the on and in the off region, because we are where we measure the background, we are still in an area where there's some dark matter, and so we have to account for it. And NB is the expected background in the on region. Alpha NB is the expected background in the. In our case, alpha is equal to 1 because the two regions have the same size. And then to put our 95% confidence level upper limits on the annihilation cross-section, we use a log likelihood ratio test statistics. And here there are the results. We have modeled the gamma line as a simple Gaussian with width 10% of the energy, like our resolution. We have our expected limits in black here, observe the limits in red, and the previous limits from 2013 in blue, and the 1 sigma and 2 sigma containment bands, which include also some systematics. And we see that we can span now a range from 300 GeV up to almost 70 TeV. We have our best limit around 1 TeV down to 4 times 10 to the minus 28 centimeters cubed per second, and we improved around 1 TeV our previous limits of a factor 6. And then we can go to the other experiments we have here. MAGIC that cannot look at the galactic center, so these are limits with SEGWA1, and of course they are less stringent. We have tested an NFW profile, and here there's Fermilat. And at a few hundred GeV, we become competitive with Fermilat. We have an overlap, and together we can put the most stringent limits on the annihilation cross-section for dark matter in the GeV-TeV mass range. After publishing this analysis, we got in contact with Tracy Slater, Nicholas Rod, and their colleagues, and we have decided to collaborate to test their latest calculations on the WINO. So they computed the WINO spectrum at the NL using an EFD expansion close to the endpoint region, so where the energy of the photon is close to the dark matter mass. This scheme summarizes the different contributions that introduce a non-perturbative Sommerfeld effect and perturbative Sudakov double logarithm. And if you are interested in more details about the computations, please instead of asking to me, look at the paper. And so here there's the line which is a pure delta function and this endpoint contribution that I have computed in yellow without considering yet the energy resolution of the experiment and so on. And then I took care of the more experimental part, and I've produced some S1-like distributions of event that you can see here in black. This is a rate. We have decided to make a very simple modeling of the background. We use the spectrum for cosmic ray protons, helium, and electrons, and they included a 10% rejection factor for the hadrons. And then we have considered 3 different signals. The line-only signal, which is in blue here, the line plus this endpoint contribution in light blue, and the line plus endpoint plus the continuum here in red. And then to go from the spectra to the expected number of events in H.E.S.S, of course, we have to consider the observations and the experiments. So the lifetime of observation, the energy resolution of the experiment, and also the effective. And these are the results. These are limits on the annihilation cross-section, again, as function of the dark matter mass. For the line only in blue, line plus endpoint in light blue, line plus endpoint plus continuum in red. And as you can see, the endpoint gives an important contribution to the line. It is a 40% at a 2.3 TeV, and it becomes a factor 2 at a 9 TeV, and even larger at higher energies. The continuum gives a less important contribution, just an 8% at a 2.3 TeV, and up to 30% at a 9 TeV and above. And in the other plot, I put just the complete line plus endpoint plus continuum limit with the containment bands, which are computed in the same way as for the real H.E.S.S analysis using Poisson realizations and including some of the systematics. You have here the thermal winner dark matter mass, and here the predicted cross-section. And you can see that with S, we could probe a very important range of mass for the wheel. Then we decided to test different dark matter profiles. So we have tested cores between 300 parsec and 5 kiloparsec, built in such a way that for RC equals 0, we recover the Inasto profile. And here you have the J factors for the different cores that we tested. We saw that, of course, for a larger cores, our limits degrade. They degrade up to a factor 200 when we consider a 5 kiloparsec core. And we decided to interpret our limit in terms of limits on the core size that can be probed, in this case, lower limits. We see that for 2-3 TeV mass, we can exclude several kiloparsec cores, while at higher energies, we exclude the smaller cores or none at all. And then we have also decided to test the strategy that we have decided to use for S2. We are doing observations at a larger latitude, so we will increase the dimension of our region of interest. And so we have recomputed the limits for a region of interest of 4 degrees. And again, testing different cores. It's obvious, but we become more sensitive to larger cores. And now, instead of a factor 200 between the Inasto and cores, we have only a factor 70. And here in this other plot, you can see for a dark matter mass of 3 TeV, the annihilation cross-section versus the core size for a 1 degree region, 250 hours, like in the real H.E.S.S analysis. Doubled statistics in the same region, or 250 hours homogeneous on 4 degrees. And we see that if we want to start to test the cores, it is more promising the new strategy, and we should really go for a large region of interest. And so to summarize, with H.E.S.S, we have put the most constraining limits on the annihilation cross-section. So far in TeV mass range, we go down to 4 times to 10 to the minus 28 centimeters cubed per second at 1 TeV, assuming an elasto profile. And our limits complement Fermi-Lat. And then with our mock analysis, we show that H.E.S.S is able to probe the WINO in some mass ranges, even for cores up to 5 kiloparsec or more. And we also saw that we improve our limits if we consider the full spectrum. And also that a good strategy for the future will be to use a larger region of interest. And of course, CTA will be more sensitive, and so it will be an even more powerful probe for the WINO, and maybe not just for the WINO, there's hope also for the X-WINO, maybe with CTA. And that's all.
Thank you very much for the interesting constraints and talk. Questions for Lucia?
So what we see from CTA consortium is that the sensitivity to the dark matter annihilation cross-section is about like an order of magnitude stronger. But the exposure will be about 2 orders of magnitude larger. So how can you explain the difference? I mean, the exposure, the CTA exposure will be much, much lower. It will be 500 hours, right? So that's what we have for CTA. So I just, what I'm trying to say is, I would imagine that either CTA is being very conservative about their projections, or has been over-optimistic about their bounds.
I mean,
because the CTA projections for the dark matter annihilation cross-section are not that much better than H.E.S.S.
Because they have a more exposure, but when they say 500 hours, they are flat over 5 degrees. So it's more in this new approach. So
I'm also not sure that we're looking at the same thing, because this is in gamma-gamma, and I don't think the CTA is
no, in CTA there's no limit in gamma-gamma yet.
It's a generic cross-section, so you have to rescale by approximately 2 or 3 orders of magnitude.
Yeah, to the continuum, I saw that there's a factor a bit more than 10. But yeah, the double exposure means just a 40% better limit, which is not a lot. They should improve because of the technique, because they look at a larger region, but a factor 10 to 20 is reasonable, I think. And then it changes depending on the mass.
Questions? Any more? Are you sure? It's the only chance to talk to a gamma person. I had a question, but it's been partially answered, so I don't think it falls in. Anybody else? Then we can thank Lucia again.
Hello, hello. Yeah. All right. Okay. All right, so good afternoon, everyone. I'll be here close to Fabio, professor /IT technical support Fabio, in case of any problems. So before I start my talk, I'd just like to advertise one workshop, one event, one conference that will take place in Brazil next year for those who are in the audience. One will be located at IIP, International Institute of Physics in Natal. If you see, it's a completely different environment from the building at ICTP. And one will be focused on more towards particle physics, dark matter, neutrino physics, model building, lepton phase violation, and so on. And one is more closer to this one, where we'll be focused more on these dark matter / cosmology connections, talking to you about neutron star phase transition and so on. So this one will be at ICTP-SAIFR, and this one at the IIP Natal. So just for those who are not familiar with IIP Natal, so if you just take Google Maps, this is the International Institute of Natal, this is the ocean. So the environment is very, very different from here. I cannot complain, I might say. These are the dunes of Natal, so that's where Daniel works, so he lives. So he talked about the Bimanizal model, so he's there in the audience, so he lives right there. And that's me, where I live, and that's where Clarissa lives when he talked about the dark photon portal. So these IIP guys, you sort of know where they live. So it's quite nice. So let me begin. So today we've seen several aspects of dark matter. We've seen people talking about have new direct detection tools, raising their flags for direct detection tools. Raising the flags for baryonic effects are important in cosmological simulations of dark matter. We've seen people talking about their limits are stronger at a given primary space and so on, as far as direct detection and indirect detection is concerned. We've seen people talk about freeze-in and people saying freeze-out is better. And we've seen people talking about extensions of the standard model in the B-Manozal and Hidden Valley extensions. So, but in my talk, I will take an orthogonal perspective, okay? My talk will be concentrated in this guy over there. I just want to know, considering that everybody has done their job, so there are smart people behind these raised questions and concerns, my talk will be more concentrated on the nature of dark matter itself. So what I'm interested in this talk is, can I ever know the nature of dark matter and have any information, grasp any information about the nature, fundamental nature of the dark matter particle? Can I ever do that? So that's my goal, okay? So let's start. So if at least everyone here remembers this line, I'm satisfied. So it's my goal throughout this whole talk, it won't take long, I have very few slides, is that we can possibly, if we are lucky, under certain assumptions, unveil the CP nature of dark matter and using gamma ray lines. So the answer I was trying to answer was, what is the nature of dark matter? Was quite hard. And so let's go down a bit. So CP nature of dark matter. And it was possible if I use the gamma ray lines. So I'm going to show you how. So in more technical terms, what it means that I want to know whether the dark matter particle is a scalar or a pseudo-scalar, and whether the interactions violate CP. So just to make sure that everybody's on the same page, we've seen this today several times, the dark matter annihilation cross-section, the flux of dark matter annihilation cross-section. The dark matter annihilation depends on the annihilation cross-section, some J factor, and is inversely proportional to the squared mass. And for the decay, you just replace the annihilation cross-section and mass squared by the lifetime and the mass, simply because one, you have the flux is proportional to any chi squared, any chi being the dark matter number density, and this one is just linearly proportional to the dark matter number density. And that gives rise to these differences. And the first question that came to my mind is that what can we do with the gamma ray flux? So we've seen bounds today on the dark matter lifetime or the dark matter annihilation cross-section. So we can do that, fine. Then the limits are stronger depending on the telescope you use, depending on the channel you got, depending on the target you aim at. You can also do, with the gamma ray flux, you can find best fit regions if you do observe a signal. So we've done this in the past. So Christopher, who is here in the audience, has done this in the past. For instance, for the GV axis observed in the Galactic Centre, where you can find the best fit regions in terms of the sigma v in the y-axis and the x-axis. You have the dark matter mass there, and here the annihilation cross-section. So you can find best fit regions if you observe a gamma ray axis. So we've done that, fine. And we could do the same thing for if we ever observe a signal from dark matter decay. And then you find these blob regions depending on the life channel you have, for instance, similar to what Arman mentioned today. It's working? I'll go there. No, that's okay. I will press in. And we've done that already. So when we did observe the controversial X-ray line, and we could find some best fit regions for the lifetime that could explain the X-ray line. And depending on the energy resolution of the detector, this blob is large or is very, very small. And that's related to the energy resolution of your detector, how well you can reconstruct the energy of that photon or X-ray emission, whatever. That's fine. But that's not, I'm not satisfied with that. What I want to do is I want to go a step further, or at least let's see if I can do that. Can I take a step further? Can I know anything at all about the nature of dark matter? Not just knowing the flux and the mass, not just knowing the annihilation cross-section and the mass, not knowing the scattering cross-section and the mass. I want to know something beyond that. Because if you give me a model, say, Fernando, I observe a signal in my detector. If I ask you as a theorist, what's the annihilation cross-section and the mass? Give me a week, I'll give you many models that can come up with that number. But I want to have a more handle properties, fundamental properties of that fundamental particle. Then it gets harder to explain or to accommodate some signal. So just to tell you that throughout this talk, I'll be including the energy resolution of my detector. Okay, so just assume that's a Gaussian, like the case. For instance, in my case, I'll be focused on Fermi, which has an energy resolution of about 10%, 8% actually at 100 GeV, and 10% about 200 GeV. Come on. Okay, so let's start. So imagine that's my assumption number one. I have a dark matter particle which is a scalar, and I want to have gauge invariance. I want to preserve gauge invariance. And the most general Lagrangian you can write down for dark matter decaying, which preserves gauge invariance, is that one for a scalar dark matter. For Fermi, it's different. For instance, I would be like Francesco has mentioned the operators that could give rise to that. But for a scalar, that's that one you have. From that one, you can conclude two things. So if B is the strength field tensor of U1 in the standard model, gauge group, and W mu nu is from SU2. And the tilde is the dual of the corresponding field tensors. So if B and D in these Lagrangians are 0, then this scalar is a proper scalar. What I'm trying to say is the CP even is scalar. And if there A and C are 0, and then phi would be a pseudo-scalar, like the axion. Any other situation different from those I aforementioned, you could imply CP violation. So that's it. That's the whole idea of the paper. and the rest is just calculation. The idea relies on the assumption that I have a scalar dark matter particle which decays. And it's singlet under the standard model gauge group. That's it. The dark matter is a scalar under the standard model gauge group, is singlet under the standard model gauge group, and is a scalar. Everything else comes automatically from that. So you just can compute the partial decay rates for each one of them, but it's just going to show you the results because they're something that you can capture. So from these ones, maybe you haven't noticed, but because of that Lagrangian, I can only have 4 different decay channels, which are gamma gamma, gamma z, WW, and ZZ out of these operators. Therefore, imagine that I'm in a situation where the branch ratio of, let's say, phi to gamma z is 20%, and gamma gamma, phi to gamma gamma is 20%. So I'm here. And the other channels, these ones are about 60%. So I'm here in this plane where this one is the branch ratio summed for WW and ZZ. This one is gamma z, this one is gamma gamma, gamma gamma. So I'm here in this point there, and here in this point here, where the sum of the branch ratios is equal 1. So there are only 4 channels. What I can conclude from this, if I'm here and there, nothing. Why I'm saying this? Because if I have 4 decay channels, gamma gamma, gamma z, WW, and ZZ, well, ZZ would not take place for this mass, but just for generally speaking, you couldn't conclude anything out of the Lagrangian. However, if you are anywhere in this green region or in these blobs, ellipses, red or blue, you can either conclude that that phi, that scalar, that dark matter particle is a CP even, CP odd, or a CP violating. So I'm saying if you have the Lagrangian with 4, that's assumption number 1. Phi is a scalar, singlet on the standard model gauge group. That's the most general Lagrangian you can write down. And you can conclude that there's some regional Prime space. There are correlations between the decay channel of the dark matter particle, which you can use to extract the CP nature of that dark matter particle. That comes, yes? Great question. Let's go back to this one. If we observe tentative gamma ray lines from dark matter decays, so I'm assuming we observe a gamma ray line. So it's a line, I can still have uncertainty that's like yours, but then it's proportional to the energy resolution of my detector. So, but now let's take another benchmark point, just for concreteness. Let's say I'm here where the branch ratio into gamma gamma is about 50%, and gamma z is about 25. And this one, 50% here for gamma gamma, and 25 also for the other channels. So I say, okay, for now, maybe I cannot see from this plot. It's hard to see, it's hard to understand. But let's see if you can understand from this one. So I'm saying that the branch ratio into gamma gamma is 0.5, gamma z is 25, and WW is 25%. So that's what you get. You get a double line. The ratio between them, the peaks, are fixed. The separation between them are fixed. Obviously, the poorer the energy resolution of the detector, the harder it is to distinguish these lines. But I'm assuming 10%, which is the current Fermi resolution. So I'm not considering something like in 10 years or 15 years. I'm using current detector technology and performance. So you can observe this. I'm pretty sure that that's for the dark mass, okay? But that's the idea. And if you might ask, okay, for now, for different masses, what happened? It gets tricky. For instance, for 20 GeV, if you compare this one, see, there is a large region where the CP even CP odd can be distinguished from one another. For 160, 165. For sometimes it works. And for 200 is harder, and for 500 is just impossible. impossible to distinguish CP even from CP odd, but it's not impossible to claim CP violation. What I'm trying to say is, if you ever work in a model which is decaying, and that guy is a scalar, singlet on the standard model gauge group, you might conclude whether or not the dark matter violates CP. So indirect detection, my bigger claim here is that indirect detection experiments can go beyond placing a limit and find best fit regions. Can actually claim whether or not the dark matter is CP violating, or what's its CP nature. So that's the biggest claim throughout my talk. So just to conclude, as I said, everybody like myself is eager to have lunch. And you just should remember that we might, if we are lucky, so these are the assumptions I've made. If you break these assumptions, it gets harder. So we are investigating now how robust our assumptions are. We can indeed go beyond the limit and best fit regions and claim whether or not the dark matter violates CP. So thank you for your attention.
So you're assuming that the dark matter decays into I think this only 4 channels, but you cannot avoid
up to dimension 5.
Okay, yeah, but you cannot avoid the scalar to mix with the Higgs, so you'll have all the other channels as well.
For the what?
The dark matter to.
If a scalar, you won't write down be up to dimension 5 with the Higgs. Is the dark matter particle is a scalar. If it were a fermion, then you were right, but it's a scalar. The scalar, if you want to talk to the fermions for the Higgs particle, you have to go to a dimension larger than 5. It's a fermion, then it's fine. Then you can do it. But for a scalar, no.
So you mean that naturally you can have only these 4 decaying
4.
channels?
Up to dimension 5. For instance, we've done for the dimension 7 already. So we were supposed to put in the supplemental material of the paper we investigated. It means that then my conclusion holds, but if the energy resolution of the detector is like 1%, which is sort of this gamma 400 experiment is supposed to, if ever happens. So the idea still holds, but it gets much more complicated if you go beyond those 4 decays.
Parialdo.
Yeah. Sorry.
Can I go? Okay. Can you please go to the slide when you had the double lines? Yeah, okay. So here, if I understand correctly, I mean, in the end,
10% energy resolution for that one.
Yeah, so I'm not worried about but for example, how do you measure the branching ratio to WW?
That's a good question. That's perfect. So that's the point. So if the dark matter has some invisible decay, then it's done. So everything I've just said, then you cannot ever prove whether CP is violating or not. The only way you can do that if you have these 4 decay channels and whatever else is visible somehow, and it's not very important.
So you don't measure, you just say that.
Yeah, the only thing you can measure for the dark matter decay is the partial decay, right? So for instance, if you observe in gamma, they only say it's the partial width.
Can you have a direct measurement of the WW branching ratio? No, because
it's that one alone, no.
And how do you claim that the one coming from gamma Z actually comes from gamma Z? Because in the end, you only see 1 photon.
Where? What do you mean from this one?
So I mean, you see 2 peaks.
Yes, one gamma. Yeah, so it
could be something. So, does it tell you that it comes from a process where you have a gamma and a Z in the final state?
No. So if you see an axis, you never know whether the axis is gamma or gamma Z or gamma whatever, because the only thing you see is photons and it's peaks.
Exactly.
Right. So that's what I'm saying. What's that? Yeah. So it's peaked on the dark matter mass, but actually you don't know the dark matter mass. You can mimic that signal somehow, right?
There could be other reasons why you have 2 lines.
So that's why this conclusion is based on that assumption from the very beginning, which is Lagrangian is that one.
You start from a model and
So if you start from a model which has something like that, then it's true. But you can mimic any signal somehow.
You assume that the dark matter candidate is one scalar.
One scalar.
This
singlet
is
on the standard model gauge group.
can be real, complex. Do you can differentiate if the scalar is real or complex? For example?
No, we are not focusing on whether it's real or complex. We're just focusing on whether it's a proper scalar or a pseudo scalar. By having the tilde, because it's like an axiom, the axiom coupling is F min u tilde is not F min u. This is the same reason. Just by CP violating. You apply the CP properties of the Lagrangian, you know that violates CP. Yes?
Maybe could you say again, I think I missed the argument, so the punchline at the end, even, so let's say the hardest case of a 500 GeV, okay, the highest mass, where
because the partial width.
Can you go to the slide? Just
this one.
So
this one.
Yeah. So on the right. So I think you said that even on the right, when let's say the blue and red ellipses fall on top of each other, and then you have all these green points in between. Your claim is that you can still tell that
it's CP violating.
So what?
But you cannot distinguish between.
So what is the argument for this statement?
What did I what?
How do I see in your plot that I can tell?
So you see, everything is in green CP violating. So what I'm saying is...
So let me just understand. So to be only CP, even I have to be exactly on the red line?
Yes.
Okay, so if I'm inside, then you have a mixture of the two.
If you're outside, you cannot say anything at all.
All right.
Yeah. So I'm saying, if we are lucky, if my assumption is valid, if you have a scalar singlet, I'm saying that's how hard it is and tricky the question is. But for me as a theoretical physicist, my question, we started this project saying, I don't care how hard it is, how hard it's going to take. I just want to know, can I ever do this? Yes, but I have to be extremely lucky.
Any more questions for Far? Yes, behind you.
Yeah,
Manuel. More questions.
Yeah, is this Lagrangian compatible with the stability of this dark matter candidate? There are
no, the dark matter is decaying.
Always decay, but what about relic density? How you can?
No, we haven't thought about relic density in this model. It's just we wanted to test whether you can claim or not CP violating CP even or not. We don't have a full model for the dark matter.
Ah, okay.
But the lifetime of this dark matter particle will be extremely large because I started with one suppressed Planck operators, if you see there. So you get 1 over Planck mass. So this lifetime will be huge.
Okay.
I can just tune what A and B, C are to normalize to get a lifetime which is not excluded. That's not the
last question for Farinaldo.
Yeah. So I guess you need a massive signal to get to the point where you can start. So you need to see the line and the gamma gamma, the gamma z, the continuum.
Mm-hmm.
To know it's a decay, you need to see the morphology.
Yeah. Precisely.
But then you also want to do, so basically you're doing what the Higgs people wanted to do when they discovered the Higgs at the LHC, look at the different channels to then say, is it CP or CP?
Mm-hmm. Mm-hmm.
But with the Higgs thing, you also had the option that it was a spin 2 decaying.
Yeah.
So what happens if this is spin 2? Can you then lie? So it's a spin 2 dark matter particle decaying to 2 lines. Can you lie in this white bits of the parameter space then?
No, I don't think so, because then you can, if it's spin 2, the operators will change, because for instance, and then this thing breaks down.
Well, but you still have decays to lines, but I mean...
Yeah, but you have other decays. Then we'll go to the same question he asked. So if you have more decay channels, the better is the resolution of my detector that I need in order to distinguish these 2 lines. One more?
Is it quick?
Yes. But it's true, for instance, if you think about it, when we had the 130, the GV line from... We observed a gamma ray line. Is a gamma ray line, or is gamma z, or what? So it gave rise to the whole discussion. But the morphology was saying, maybe it seems to be annihilation. For instance, for the GV axis, we know its annihilation cannot be a lifetime because it would be too small. But it would be something like towards you saying.
Just quick comment. Maybe you can say something also about the annihilation case, not about the nature of the dark matter itself, but about the nature of its interactions. Like if you have a fermion and you have a scalar or pseudo-scalar current coupled to this gauge field strength, you can say if the interaction is CP violating or not.
Yeah, maybe. I haven't thought about it.
I really think this is something that's going to take some time, so maybe you can discuss it over lunch while we discuss other things over lunch. So I think it's really time to thank Farinaldo and all the other speakers of this session today and for the entire workshop. So I might as well wrap up this thing. I wanted to try the crown to see if it's really so complicated to talk in this, but I'll try it next time. Manuela, is there anything specific you want to say? So first of all, let me apologize on behalf of Enrico, who could not be here. He apologizes. There have been things in the family he had to run, so he could not be here. He apologizes. We have done all this together, so I think it would have been good if he were here, but unfortunately he couldn't. So I would like to thank all of you for coming here. It's been, from my part, it's been very exciting, and I think the diversity of the talks and the geography really showed that we are concentrating this activity in South America as well. So it's taking shape in a big branch, in a field by itself. We have had the first edition of these 1.5 years ago, but it was in 2017, right, Manuela?
Yes.
And we were not planning to have it every single year, and that's why it was 1.5 years away, but still it was 2018. So we really believe that this activity should continue with a certain inertia in South America as gatherings putting together all the different sub-branches. But nonetheless, we will not run it in 2019 because we also believe that as a South American community, we need some support and some self-support within the continent, and there is going to be another event related to dark matter in South America in 2019. So we will come back, very likely stay framed in 2020, but in the meantime I would like, Daniel, if you can come and tell you why we're not going to be gathering here in 2019, but rather in Buenos Aires.
Okay, so thank you very much, and thank you for this fantastic workshop. Okay. Dale. Soy un cantante moderno yo.
Muy bien, te vale.
Okay, several of you know very well this the Dark Side of the Universe workshop that's taking place since 14 years ago. Next year is going to be the 15th edition. In 2012 was in Brazil, was in Búzios, and this is going to be the second time in South America. And let me explain briefly. That is going to be taken in Buenos Aires, in Buenos Aires University. This university is one of the most important of South America. Other very important universities are here in this country, not in Brazil, but the University of Buenos Aires is one of the most important also of our continent. And Buenos Aires is a very nice city. It's very well communicated. You are not going to have problem to come to Buenos Aires. You could take the airplane. In 3 hours you are there. There is no excuse to not come. Okay, yeah. Brazil is small, you know. Okay, a bit more. You are in the north of Brazil, but. But okay, it's true that this is not only for South American people, but I am talking now to this audience that is from South America. And Buenos Aires is not far. You can go there. Nice city with tango, with food. You like tango? I don't like to dance tango, but I really like tango to hear tango. The people in black and white are in black and white because they are dead, no? What could I do? Tango is an old-fashioned thing, but still there are people alive that are very good. And Garello is also dead, the past year, no? This guy was in color, but now it's in black and white. But food, okay, you like meat? Come to Buenos Aires, you can eat empanadas, there de asado, cordero, you are welcome. If you're vegetarian, don't worry. we are going to try to do something, okay? There are some special vegetarian meat, and we are going to take care of you. If you are Italian, don't try to eat a pizza alone, okay? I know that in Italy, one pizza, one human being, no? But not in Argentina, because our pizza is not a pizza, really. It's a focaccia, because the first immigrant in Argentina were from Liguria. And the proof that I am telling the truth is this. This is the farinata, the faina from Liguria, okay? You could take a faina in Buenos Aires, as in Liguria, and our pizza is a focaccia with a ton of cheese, okay? If you like cheese, you like focaccia, you are going to like this strange invention that we call pizza, but it's nothing to do with the Napolitan, the pizza from Napoli, no? This is another thing, but try it because it's very nice. And the city has a lot of things to do. There are parks, there are a lot of really things to do there. And okay, one also, Cecilia Carampico, also one of the organizers, and is there. The other ones are at the moment in Buenos Aires. And this is the steering committee, you know. Most of you know these guys. Most of the people have been in the transparency, no? It's some of your collaborators, not necessary to say them. This is the steering committee. And okay, we are going to have this edition in Buenos Aires, and all of you are welcome. And also we hope to have funding to help everybody to come to enjoy the workshop. And thank you very much.
Thank you very much. I gather that the scientific program is not still up. The focus at the moment is more on the logistics, I understand.
But the scientific program is, as usual, in this meeting that is going to be dark matter, dark energy, also neutrino physics. We are going to, Cecilia is more from the cosmological side, and we have cosmology, astrophysics. We are trying to cover everything, no? Then it's try to be as everything you related with dark energy, dark matter, and also dark sector, neutrino physics is welcome, okay? And we have cosmology, we have astrophysics, we have everything.
Muchas gracias.
A ti.
So I think unless anybody has anything specific to say, we can close the meeting here, thanking all of you for coming all the way. We're going to go for lunch and reconvene here. I'm going to estimate that probably 30-ish people are going to come, but to try and be there. Who thinks about coming tonight? Can you raise your hand? Okay, that's not going to be exceedingly big. I can figure this out. If you can try and be there by this time, that's going to help for not being kicked out. It's a good approximation, because you'll just need to get the green line and then walk, so it should be okay. Then maybe you can coordinate privately, but before, if you get into the metro before 5, it's okay. Try and be inside the metro before 5. And again, thank you very much, and have a safe, Tony.
I propose to thank the organizers.
Thank you very much, and for those of you traveling today, have a safe trip. The others, no.
Don't have a safe trip.
Thank you.